Hey everybody, I think this is notes number 30, and today we're going to be starting the applications part of this course. And the type of application we'll be working on all this week is called related rates. Now the first few problems, I think 1 through 7, are not really related rates applications, but they're just problems to get us ready to do the applications. So problem number 1, differentiate with respect to x. Okay, so x is our variable, and we're assuming that y is a function of x and z is a function of x. So we're going to use implicit differentiation. So for the derivative of x squared, we have 2x. And for the derivative of y squared, we have 2y times y prime. Remember, the other way to write it is 2y times dy dx. And for this kind of problem, I'm going to use the dy dx kind of notation. And then in a similar way, the derivative of z squared would be 2z dz dx. The derivative of z with respect to x. So notice that this equation that we just got from differentiating has two rates in it. dy dx is a rate and dz dx is a rate. So these two rates are related. So this is an example of a related rates equation because it has multiple rates that relate to one another. Number 2 looks very similar to number 1, except it says differentiate with respect to t. Okay, in most of the problems that we're about to do, your rates have to do with time. Miles per hour, centimeters per minute, things like that. And so time is going to be our variable, and usually we use t for that. So let's assume that x, y, and z are all functions of t, and we're going to use implicit differentiation. So the derivative of 2x, or of x squared, would be 2x dx dt. The derivative of y squared would be 2y dy dt. And the derivative of z squared would be 2z dz dt. So there's an equation that relates 3 different rates. And let's just imagine that you were solving for one of those rates and that you had enough information given to plug in the rest of the numbers. You would plug in all the other things and you would solve for the one you don't know. So that's where we're going to be headed when we get to the applications. Here's another one. Now this uses a formula. By the way, the previous one uses a formula as well. Does anybody recognize that previous formula? That could have been the Pythagorean Theorem. So maybe this is a problem that has to do with a right triangle. Or it could have been the equation of a circle. Now number 3, that looks like the formula for the volume of a sphere. So let's imagine that you have some sphere and that it is growing or shrinking with respect to time. V is volume, R is radius, and when we differentiate this, we would get an equation that relates the rate of change of the volume to the rate of change of the radius. Okay, so on the left side, the derivative with respect to t is going to be dv dt. And on the right side, the derivative with respect to t is going to be 4/3 pi. Now don't be intimidated by pi. Pi is just a number. So you can think of your constant as 4 pi over 3 if you want to. Leave your constant and then multiply by the derivative of r cubed, which is 3r squared dr dt. And because we have a 3 in both places, top and bottom, we can go ahead and reduce this, simplify it, and we get dv dt equals 4 pi r squared dr dt. 4 pi r squared dr dt. Okay, let's work through several other examples where we're given some formula or some equation and we're going to differentiate with respect to time t. So, do you know this volume formula? That's right, this is the volume of a cone. Pi r squared represents the area of the circular base of the cone. H represents the height of the cone. Now let's say for this problem that the radius is constant. So maybe the cone is changing size, but it's only changing size because the height is changing. The radius is not changing. Now let's differentiate. So we have dv dt. And then on the other side of the equation, because r is a constant and pi is a constant and 1/3 is a constant, this whole quantity here is our constant. So we have our constant times the derivative of h, which would be dh dt. Now in part B, same idea, we have the formula for the volume of a cone, but let's suppose this cone has a constant height. So it could be that the size of the cone is changing, which would change the volume and the radius, but it's just changing because the radius is growing or shrinking and the height is staying the same. So then when we differentiate, we get dv dt equals, now for this one our constant is 1/3 pi times h. We could just call that pi thirds h if we want to, or 1/3 pi h. And then the variable part is the r squared. So its derivative is 2r dr dt. And then to simplify that, we have 2 pi over 3 times h times r times dr dt. Now in part C, we're still working with the volume of a cone. And I'm doing this one with you because there's a lot of these applications that involve the volume of a cone. It's one of our favorite types. In this one, r and h are both variables. Neither one is a constant. So you have a constant, 1/3 pi. You have a variable expression r squared multiplied by a variable expression h. So because that's a product of two variable expressions, we're going to use the product rule to differentiate. So let's start with the derivative of the left, dv dt, and then the constant times the derivative of r squared h. So let's use the product rule. The first times the derivative of the second plus the second times the derivative of the first. Okay, and then maybe, depending on what we were going to do with this, we might do a little bit of simplifying. Now, when you get to the applications, you'll notice that a lot of these problems actually help you to get the relationship between the radius and the height. For example, let's say the problem told you that you have a cone, and let's say that it said the radius is always half the height. If that's the case, you could go back to your beginning equation and you could substitute 1/2 h in for r and create an equation that's only in terms of h. That could be simplified and then differentiated. So if you're only interested in the derivative of h and the derivative of v, you could do something like that. Or let's say that you want your equation to be in terms of r, not in terms of h. Going back to here, multiply both sides by 2, and you could replace h in your equation with 2r. Do that first before differentiating. Simplify, and then you could differentiate that. So you have some options. You can avoid using the product rule if you think about that kind of thing ahead of time. Okay, we're going to do these three. And number 5 perhaps is a circle that's growing or shrinking, or perhaps is something leaning against a wall, making a right triangle. Number 6 could be some object like a hot air balloon that's rising up in the air, and we have our angle of elevation theta. We have our opposite and our adjacent. Number 7 could be the volume of a cube whose side length is s. So these are all chosen because they tie into some kind of problem you may end up doing as you do the applications. But for now, we're just differentiating. Differentiate with respect to t. So the derivative of x squared, 2x dx dt, plus the derivative of y squared, 2y dy dt, equals the derivative of 25, 0. Number 6, the derivative of h dh dt equals the constant times the derivative of tan theta would be secant squared theta times d theta dt. And number 7, the derivative of the volume, dv dt, equals the derivative of s cubed, which would be 3s squared ds dt. Okay, the second part of today's lesson is going through, I think, 4 or 5 different word problems. So what I'm going to do, just to make these videos a little bit more manageable, is to go through this one and then end this video, and then I'll do the rest in a part 2 video. All right, a 13-foot ladder is leaning against a wall. If the top of the ladder is sliding down the wall at 2 feet per second, how fast is the bottom of the ladder moving away from the wall when the top of the ladder is 5 feet from the ground? Okay, so we need to picture what's going on here. So we have the ground, we have a wall, assuming that those are perpendicular to each other, and we have a ladder leaning against the wall. So, step 1, draw a picture. Most of the time, there's something geometric going on here, and you can draw a picture. Every once in a while, that doesn't apply, but for the most part, draw a picture and label it. Some of the labels will be variables, and some of the labels will be numbers. So we know that this ladder is 13 feet long, and that's not changing. That's a constant. So I'm going to label that 13. As the ladder slides down the wall, this distance here, this vertical distance, changes. I'm going to give that a variable named y. And this horizontal distance changes as well. Let's call that x. Okay, so we drew a picture and labeled it. Now let's list what do we know and what do we want to know. So list the givens and identify what you are looking for. Let's see here. The top of the ladder is sliding down the wall at 2 feet per second. That is a rate of change. So we would call that dy dt. Now remember, derivatives are positive when the quantity is growing. Derivatives are negative when the quantity is shrinking. And as the ladder slides down the wall, the quantity y is getting smaller, so the rate of change dy dt would be negative. So you have to figure that out for yourself, -2. Next, let's figure out a way to represent the rate of change for x. So let's call that dx dt. Were we given that piece of information in the problem? Let's see, the problem says, how fast is the bottom of the ladder moving away from the wall? No, not only were we not given that, but that's what we're trying to find. Okay. And notice that there's also a condition in there. So we want to know the rate of change of the bottom of the ladder when the top of the ladder is 5 feet from the ground. So we're finding dx dt when y equals 5. Okay. So after we've drawn the picture, labeled it, identified what we know and what we need to know, the next thing we do is we need to relate the variables. So we write an equation that relates the variables. This is where your knowledge of geometry comes in. You're looking at this and you're saying, it's a right triangle. I know the Pythagorean Theorem relates the side lengths of a right triangle. So we have x squared plus y squared equals 13 squared. Remember, ultimately you want a related rates equation, not a related variables equation. So after you get your equation, you differentiate so that you can relate the rates. So let's do that. We have 2x times dx dt plus 2y times dy dt equals 0. Okay, so once we have this, it's time for us to plug in the numbers that we know and solve for the number we're looking for. And in this process, we often realize that we're missing something. So, for example, we have dy dt. We're going to plug that in. We have y equals 5. We're going to plug that in. We're solving for dx dt, so not plugging in anything. But notice that we also need to know x. So let's go back to our equation. Substitute 5 in for y. And solve for x. You're going to find that x equals 12. I'm just going to fast forward to that. So now let's substitute all the numbers in. So we have 2 times 12 times dx dt, we don't know, plus 2 times 5 times dy dt was negative 2 equals 0. Now, in retrospect, I kind of wish that when I was at this step right here, I had just divided both sides of the equation by 2. That would have simplified things for me, but I'm just going to go ahead and do it now. Divide by 2 on both sides. 0 divided by 2 is still 0. So we have 12 dx dt minus 10 equals 0. Add 10 to both sides. Divide by 12. Whoops. Did you notice what I did there? Fix that. 10/12 reduce, and we get 5/6. Now, what are the units? Let's look back. Feet per second. And here's a way to check some reasonableness, just a very general check. Notice that that turned out to be a positive rate. Is x growing? As the ladder slides down the wall, does the quantity x get bigger? Yes, it does. And because it's growing, it makes sense that we would have a positive rate dx dt. All right, so there's your first related rates example. I'm going to end this video and then record part 2, and we're going to have number 9, number 10, number 11, number 12, and that's it. So 4 more to look forward to. Thank you. See you in the next one.